The objective of this lab is to determine the mass of a black hole using the gravitational principle by observing the forces the black hole exerts on a star. The mass of the black hole was found to be 3.64 times 10 to the 31st kilograms. The momentum principle is used to determine the net forces acting on the star, and the analysis of the curving motion proves which forces are acting in the parallel direction and which are acting in the perpendicular direction. The initial values given include time, mass of the star, and position of the black hole. Other initial conditions were included in the .csv file that vidle referenced in this code. These values include initial x and y velocities and the position of the star. Starting from these initial conditions, my goal was to first determine momentum, so I could determine change in momentum, which would lead to the value of the parallel, perpendicular, and net forces. After discovering the forces, I was able to plug them into the gravitational principle, using the given positions, to find the mass of the black hole. Here is the code that I edited to predict the mass of the black hole. First, I changed the mass of the star, which was given in the problem. I changed delta t to equal 60 times 60 times 24 to equal the number of seconds in a day. Delta x was initially given, but not delta y, so I added delta y and y velocity, which was necessary to predict the velocity and momentum vectors. I changed v initial to equal x velocity index minus 1 and y velocity index minus 1, and changed v final to equal x velocity index and y velocity index. The velocity in the x direction was 0. Using the values for velocity, I was able to predict the star's momentum. P initial was equal to the star's mass times its initial velocity, while P final was equal to the star's mass times final velocity. Delta V, or the change in velocity, therefore equals V final minus V initial, while delta P, the change in momentum, equals P final minus P initial. The change in momentum over the change in time is equal to delta P divided by delta T. F net is equal to dp dt by the momentum principle. P hat is equal to P initial divided by the magnitude of P initial. The magnitude of dp dt parallel equals the magnitude of P hat times the magnitude of P final minus the magnitude of P initial, all divided by delta t. dp dt parallel equals P hat times the magnitude of dp dt parallel. F net perpendicular equals dp dt perpendicular by the momentum principle. I then set g equal to the gravitational constant, which is 6.7 times 10 to the negative 11th, and updated the position of the black hole, which was given in the problem. Finally, the mass of the black hole could be found by manipulating the gravitational principle. The mass of the black hole equals the magnitude of F net times the magnitude of the position of the star squared, divided by g times the star's mass. I added the function print black hole mass so the program would display the value after running the computational model. The mass of the black hole was 3.64 times 10 to the 31st kilograms. I updated the arrows so that F net perpendicular is black, F net parallel was blue, and F net was red. As you can see, F net perpendicular is pointing in a direction towards the black hole, while F net parallel is tangential to the object's path, and F net points in a direction between the two. My computational model diverged somewhat from what the experimental file predicted. The computational model did not make a complete revolution, while the experimental data resulted in a complete revolution when plotted. What does it mean? The values of F net and dp dt, of F net parallel and dp dt parallel, and of F net perpendicular and dp dt perpendicular are equal. However, the values do not represent the same phenomena. The respective forces cause the changes in momentum. These changes in momentum are what we are able to observe. What if the black hole is replaced by another black hole at the same location and it had the same effect on the star's motion, it would be impossible for the mass to differ from the mass of the previous black hole. Every other term in the gravitational principle equation remained the same, so the mass could not change. By using the initial values, the momentum principle, and the gravitational principle, I was able to accurately predict the mass of the black hole.